Okay, so this chapter is going to be generalizing the notion of integral from from one dimension, as you learned in Calc 1, to 2 and 3 dimensions, effectively. So we start off rather simply with double integrals over rectangular regions. Now, um, so first of all, let's recall that the way that integral was defined back in Calc 1 was as a limit of Riemann sum, right? You approximated a function, the area below a curve by the areas of rectangles, um, where what you do is you take the interval that you would integrate over and you subdivide that interval into however many pieces, n different pieces, and then each rectangle would have a width, delta x, which was something that you could compute. We assume that we just split up the interval evenly into subintervals, and then for each subinterval you would choose a representative height that would be the xi, and then plugging that in gives you a corresponding height for that rectangle. So you had like left hand approximation, right hand approximation, midpoint approximation. All of those were ways of describing uh, Riemann sums, and then as you let the partitioning go to infinity, as you let the number of subdivisions go to infinity, this calculation of area would closer and closer approximate the actual area below the curve, which would be the definite integral. The book shows that this can be extended to the two-dimensional case, and I'll illustrate it briefly, but we're not going to go into too much detail with it. The idea is that, well, because we're working over rectangular regions, and that'll change in the next section, but for now, we assume this nice situation where our double integral is occurring over this kind of rectangular base, um, with x ranging from a to b and y ranging from c to d. That's what this kind of, I guess you could call it a Cartesian product. You're taking a product of two different intervals here, creating a subset of R2, and then you have a surface that sits over um, this base, and then mm, the two-dimensional integral, or the double integral, would be measuring the volume below the surface. And the idea is that the definition could be the definition can be a Riemann sum, just as in the one-dimensional case. You would subdivide this rectangle into sub-rectangles by subdividing along x and subdividing along y. That would be the m and n in this. And then um, for each subrectangle, you could then determine a corresponding height, which would then be the height of the rectangular prism uh, that sits above that subrectangle. And then as you let the number of subdivisions go to infinity, that will closer and closer approximate the volume that is below the surface. So this is a rather formal definition, but of course we're not going to really be using that when it comes to integrating things. We'll do the same kind of um, thing that occurred with Calc 1, where we've realized that an integral can be evaluated by um, finding the antiderivative and evaluating at the endpoints, right? That was the result of the fundamental theorem of calculus part 2, said that we had this relationship. So instead of computing things as Riemann sums, we can find the antiderivative and use that. So a very convenient thing to have with us. I guess one thing I should mention here, this dA. So these differentials are things which can be confusing when you are first introduced to them. dA is supposed to be an infinitesimal piece of area. Okay, and so this will be rewritten depending on what kind of region you're talking about. For right now, we're dealing with flat things, and so we can rewrite this as dx dy or dy dx. And the order will dictate the order that we are doing our integrations in. I think I have a picture of that below. Um, eventually we will do double integrals over surfaces where this will no longer be flat, and this will slightly change. Uh, we'll talk about that when we get there. Okay, in this paragraph, I'm just saying that just as how in the one-dimensional, uh, for for integrals of one dimension, um, it measured the signed area. So if you had parts of your curve that dipped below the x-axis, this piece of area was treated negatively. Same thing happens with surfaces. So if your surface dipped below the xy plane in this picture, that would be treated as though it had negative volume. That is what the double integral is computing. Okay. Um, this example slash exercise most closely approximates what we have just been talking about. Um, so the idea is that instead of computing an integral by actually doing integration, you can sometimes think of it as corresponding to the volume below a surface. So um, in this problem, you're given this function z is equal to the square root of 9 minus y squared. I've only modified your problem in terms of numbers, basically. So this 9 is a different number, and the rectangle that you consider this surface over is slightly different. But what makes this bothersome to actually integrate, if you were to spell out the actual integral, you could maybe write it like so. So what I'm doing here is I'm letting x range from 0 to 2, as it is supposed to do, and y range from -3 to 3, as it's supposed to do. And now the issue is that, well, we can get rid of, so here I'm doing a bit of a trick. There's a property that I'll point out in a moment, where because this function um, doesn't have x uh, at all, you can actually split this into a product of an integral involving x and a product of an integral just involving y. Really, the idea is that this is a product of two separate functions. One, it's really more well. Let me just scroll down to it really briefly. So it's this property. If the function is one where you can split it into something that only involves x and something that only involves y, like this, then what you can do is you can separate out the you can rewrite the integral as a product of two one-dimensional integrals, like this. So where x ranges over what it ranges over, and y ranges over whatever it ranges over. This relies on two things. This relies on the fact that the original function can be written as a product of x and a function of y, and also that you have a rectangular region. So it's important here that you have a rectangular region. If you had a slightly different type of region, such as the ones that are in the next section, then this doesn't hold. Okay, but in this situation, so we do have that here, right? There is no x, so really you're integrating over the function 1 um, for x, and then for y you have the same function here. And then the problem is to do with this function. If you were to try computing this by hand, I mean, you could. This is actually a type of integral that you encountered in Calc 2. This would involve trig substitution. You would substitute y with 3 sine of theta, and then inside here you would get 9 times the quantity 1 minus cosine squared, or 1 minus the sine squared theta, and you could rewrite that to be 3 times cosine squared theta. You can take the square root of that and then continue. But that is not necessary to do, because this is a definite integral, and this function should give you mm, it has a geometric description that you should be familiar with. This is a half circle, right? This is the upper half of a circle of radius 3. And the fact that we go from -3 to 3 means we capture the entire half of the circle, as you can see in this picture. In your question, you actually go from 0 to whatever the endpoint is, and so you end up with a quarter circle in that case. But yeah, here I have a half circle, and so the point is that instead of doing the integral as an integral, we can instead think of it as volume of a geometric object, right? Namely this half circular cylinder. So you would just do base of the region times the height. The height in this case, I'm treating it as this extending in the x direction of length 2, and the base is going to be half of the area of the circle. So 1/2 pi times radius squared. Radius is 3, so 9, and this gives you 9 pi. So I don't need to actually integrate in this question. So that's the point of this exercise is instead of integrating, you can think about it visually and use your volume formulas from geometry. Okay, now for some properties of double integrals. So I would say that all of these properties are intuitive. So they should make sense to you. First of all, we have, well, the first and second properties are what I would call linearity. So the fact that you can split the double integral over terms, right? You can see that in this equation, and that you can pull scalars out of the double integral, right? Both of these properties are something that you'd call linearity of this operator. So it was true for one-dimensional integrals. It's true for two-dimensional and three-dimensional. It's true for integrals in general. Okay. For number 3, we have so this is analogous to this property that you knew from one-dimensional integrals. So in the one-dimensional setting, you only have intervals to consider, right? Intervals on the number line. And so an integral from a to c can be split up into an integral from a to b and an integral from b to c. That's what I'm trying to write here. Well, it's more difficult to express this idea in 2 dimensions and higher because it's not simply an interval that we have, but it can be some arbitrary regions. But the point is that we would take a region of 2-dimensional space and we just subdivide it in a way where they don't overlap. That's what this condition means. Their intersection is empty. And that they together form the entire region you're considering. So you can see that this is the analog of this one-dimensional property, that you can subdivide a 2-dimensional region into these 2 regions, and the integral over the subdivisions, when you add them together, will be the integral over the total region. That's what this is saying. This is common sense, but I'm fairly sure that this is not something that we'll use, but it should make sense. So if the function f is always greater than or equal to the function g on whatever region we're considering, then of course the double integral should be greater. The double integral for f should be greater than the double integral for g. Think about the fact that double integrals are volume. So if the function f is always above the function g, then of course the area or the volume below the function f will always be greater than the volume below the function g. I tried to illustrate this, but it's a little, this 3-dimensional picture is a bit unclear, I think. But hopefully you can visualize in your mind that, yeah, if f is always above g, then the volume is always going to be greater as well. Okay, 5 is sort of recasting 4 into a very particular situation. So little m and big M are supposed to be the particular constants, particular numbers. Like, take them to be the maximum value and the minimum value of the function f on the region R that you're considering. So then, of course, if you take the minimum value of the function and you create a rectangular prism out of that, the area of that, or the volume of that rectangular prism, is of course going to be less than the volume below the surface. And if you take the maximum value of the function, and you create a rectangular prism out of that, of course the volume of that rectangular prism will be greater than the volume below the surface itself. That is what is represented in this set of inequalities, right? So this is the volume below the surface, and this would be the volume of the rectangular prisms. So the A is standing for the area of the region of the base that you're integrating over, and so this is the volume um, of the rectangular prism, matching the height with the max height or the max value of f and the min value of f. I guess I should say that they're technically, they don't need to be the max value and min value specifically. They just need to be greater than and smaller than. So you those the max value and the min value specifically would be the exact threshold for this to hold true, right? You can go greater than the max value or lower than the min value, and the property will also hold true. Okay, and last property. So this property, I would say, is fairly important because it is very useful to use in your various integration problems. I always find myself using this. Um, so yes, if the function can be written as a product of two independent functions, one that is only using the variables x, one that is only using the variables y, then I basically argue over here that this can be rewritten. So if you have a double integral that is not, so with respect, dA means that we're not specifying what integration order. So I just choose one arbitrarily. Okay. So first integrating with respect to x, then integrating with respect to y. If our function can be written in this way, then what you should notice is that h of y is something that does not depend on x. It is basically treated as a constant with respect to integration by x. And so what you can do is pull it out. It basically acts as a scalar when you integrate with respect to x. Think of x as varying the value x. And in a sense, it's to do with like the Riemann sums. As you integrate over x, you're varying the value of x and sort of recording all those heights and then summing them together. Well, h of y is independent of that variation, and so you can pull it out. And then you end up with this kind of expression. Right. Now the next thing is to group this integral with respect to x together. And so I'm labeling it as this function capital G of x. Well, it's a function solely of x, so we can do the same thing. This outer integral with respect to y varies y. This function of x is independent of the variation of y, so we can pull it out of the integral with respect to y. And if we pull the whole thing out, we end up with this, which is exactly this. So you can see that if your function can be written as a product in this manner, and if your your region of integration is nice, if your region of integration is a rectangle, then you can split it into integrals along two different lines. So notice that the bounds are based around the original region R. So the fact that R was you let x vary from A to B and y vary from C to D, that shows up in this product. I guess just as a comment for the future, when in the next section the regions will have a dependency between them. So you will have that the say like in this kind of integral here, you may have that the upper limit or the lower limit of the x may depend on y. Well, that makes it so that the region you're integrating over is no longer a rectangle, which means that you have to be more careful about doing things with the integral. For example, in this section, you're able to swap the integrals easily because it's a rectangle. When you swap the order of the integration, the limits swap as well, which is actually what you'll see here. But in the next section, you can't just simply swap things. You have to rewrite the expression that defines the region. Because there will be a relationship between x and y encoded in the limits of integration, if you try to swap the order of integration, you also have to re-express those bounds. Um, and so not only are you not able to split the integral in that situation, you can't even just easily swap the integrals. You have to do a bit of work in order to swap them. So this property is particular to rectangular regions, and it is one reason why rectangular regions are so simple to work with. Okay, right, now for iterated integrals. So what this is saying, basically, is that double integrals like this, they don't specify what exactly you're supposed to do. It's just an abstract notion of I'm just computing the volume below below a function that it sits over a particular region R. Whereas when we specify it like this, we're actually telling you how to compute the how to sweep over that region R. So here it's saying that we first integrate over y and then we integrate over x. You read this inside out. So you evaluate the inner integral first, which is why this has brackets around it. So you'd compute the inner integral first. That would give you a function that only depends on x, right? Think about it like this. If you compute this inner integral, you'll end up integrating with respect to y. Then you evaluate at y equals c and at y equals d in order to do the definite integral. So the end result will be some expression that no longer has y involved because you've already plugged in values for y. So you end up with something that only depends on x. And then the outer integral will take care of that. It will integrate with respect to x and then evaluate, plugging in x equals b, x equals a. And so then your end result is just going to be a number, right, corresponding to a volume. Yeah, and contrasting these two, the difference is that you swap which integration you're doing first. Here we first would integrate with respect to y, then x. Here we integrate with respect to x, then y. And notice that by swapping the order of integration, we also swap the bounds, right? So a to b, c to d becomes c to d, a to b. I'm probably reading that the wrong way around, but I read that outside in, but you would evaluate inside out. Okay. Um, the fact that double integrals can be split into iterated integrals. Yeah, so I don't think I phrased that correctly, but the idea is Fubini's theorem says that a bunch of different expressions are equal to each other. Namely that this double integral, where we don't specify any bounds. So this you would think of, this is the Riemann sum. Okay, this is the two-dimensional Riemann sum. Versus, well, I think even this expression isn't quite specified enough, but it's versus these two. So really, you're contrasting this double integral, which is by definition this Riemann sum, versus these ways of doing it, which you know how to do them. You treat them as iterated integrals. You evaluate the inner integral first, which is a Calc 1 thing, and then the outer integral you do next, which is again a Calc 1 thing. So the fact that this double integral, this Riemann sum, is equal to these nested one-dimensional integrals, this fact that they're equal is called Fubini's theorem. And I should make the additional comment that there are certain situations where Fubini's theorem doesn't hold, but that will be, you should not encounter that in this class. It has to do with functions where things go bad in the denominator, basically. It has to somehow be discontinuous in a bad way or blow up to infinity in some particular way. And you should not see that in the problems that we give you. So basically for this course, we can assume Fubini's theorem is true. We can assume that the the abstract double integral is equal to the iterated integrals. Okay. This picture, I think, helps to illustrate certain things. So, um, this this picture illustrates this integration order. So when you fix an x and you're calculating the area inside here, this is basically the innermost integral that you're considering. You vary along x, or no, along y, and then by computing the area with respect to y, you're integrating the function with respect to y as your inner operation, and then you would sweep this plane over the interval for x, and that would then compute out the volume. So the outermost thing is that you integrate with respect to x. That's what's happening in this picture. Versus in this picture, you can see that the planar highlighted planar region is it varies along x first. So the inner integral that you do is with respect to x, and then as your outer operation, you integrate with respect to y. You sweep this plane through whatever domain is specified for y. And so this is a way you can visualize what these iterated integrals are actually doing. They are telling you different ways of sweeping out the three-dimensional region as part of computing the volume. So they're sweeping it out in different ways. Okay. Right. And this example, so I have a bit of a gripe about your homework problems in that they didn't quite show you this property, which is that sometimes you are forced to integrate with respect to one order versus another. Well, maybe not forced, but one way it would stand out as being considerably easier than the other. In your problems, you don't have that. In fact, in I think both of your problems, the order, you could go in either order. And in fact, I think I choose to not even do either order. I choose to use the splitting property instead. Okay, so I wanted to show an example where the choosing the correct order does matter. So consider this example. You have the double integral of the function x times sine of xy, integrating over this rectangular region. So x varies from 0 to pi, y varies from 1 to 2. So if you write this as an iterated integral, you can do it in two different ways, right? So in this order, we would first integrate with respect to y, then x, and we let y range from 1 to 2. We let x range from 0 to pi, right? Just as the region specifies. Alternatively, we can integrate with respect to x first, followed by y, and you can see that the bounds are also made to match the rectangular region. Now, the important point is that the first way of writing this is easier to do. Notice that if you integrate with respect to y for this function, that will actually absorb x, because so it's to do with partials. So the integral is the opposite of the derivative, and in this case, because we're in multivariable calculus, it's the opposite of the partial derivative. So integrating with respect to y should be the opposite operation to the partial derivative with respect to y. So notice that if you take the derivative, the partial derivative of minus cosine xy, well, the derivative of the cosine will be minus sign, so that will cancel with the negative. But then also you have a chain rule. So the partial derivative with respect to y of the function xy is going to be x. So you end up getting an extra x coming out from chain rule when you take this derivative. That's why the x gets absorbed under the integration by y. It's because x actually shows up as part of chain rule. It gets canceled by the reverse chain rule, I guess. So this integral we've basically just done already. By integrating with respect to y, you end up with this quantity. You would evaluate this expression from 1 to 2. So, and notice that specifically I need to, in order to make it clear what variable it is that we plug into, I like to specify which variable in my interval. So, in my uh, the way that you describe the evaluation, right? So normally this you would write it as a vertical bar, kind of like this. I sometimes like to use brackets to see a bit more clearly what I'm doing, especially if this is like inside an integral like this. It looks a little bit better to surround it with brackets. And so, yeah, we plug in at y equals 1 and at y equals 2. Oh, I think I I didn't need this extra line. That's yeah, that's unnecessary. That's okay. So when you plug in at 2, you get minus cosine 2x. When you plug in at 1, you get minus, but then because evaluation, you have an extra negative that cancels with this negative, so you get cosine of x. So that is the evaluation. That is us computing the inner integral, right? Okay, so we end up with that, and that we can easily integrate also. Right, the integral of cosine is sine. The 2x will pop out to cancel the 2, you have to pop out a 1/2. It's one of those guess and fudge type of integrals. People that aren't comfortable with it will do a u sub, but it should be pretty clear that this is the integral of that, and of course integral of cosine is sine. Then you evaluate at x equals 0 and pi, and when you do that, everything ends up being 0. So we're able to compute this integral pretty readily. The important thing is that this integration order was easy to work with. If we tried to do the other order, which is, I don't go into detail on that, but if you tried to do the other order, you would have to start with integration by parts, and things would be rather complicated. Notice that this has two things that involve x, right? So if you were to simplify this integral back to like kind of the Calc 2 situation, this is analogous in part to, well, maybe instead of y, right, you treat it as like some number. So this inner integral is basically this guy. So this is a cyclic by parts problem, if you remember that from Calc 2. You differentiate x well, oh no, not cyclic by parts. You can differentiate x twice, and then it goes away. So this is just integration by parts. I guess doing it once will be enough. And so then you'd be able to compute the inner integral, but then the next one will be a bit more involved as well. So it's certainly a lot easier to do the first integration order. So you can see that sometimes it can be convenient to try different integration orders to see which thing is easier to compute. Okay. Now for a problem that is more similar to your homework problem. So in this example, it asks you to interchange the order of integration. And you can see that these are all numbers, which means that this is describing a rectangular region. You're integrating over a rectangular region. It doesn't matter that these are out of order. You can just ignore that fact. The only reason that it was useful to have it like that is it gets rid of a negative later on, I believe. Maybe it doesn't. Okay. Well, so how you swap the order of integration for a rectangular region is you can actually just swap the integrals themselves. So from dy followed by dx, we reverse the order. So dx followed by dy, and then you can see that the bounds also will just completely switch over. 1 to 9 from outside becomes 1 to 9 inside, and 4 to 2 becomes 4 to 2. After you do that, you can integrate the inner integral, or compute the inner integral. So let's see. The over y squared is treated as a constant. So really this is, you just think of it as a times the square root of x integrate dx. that's how I'm considering this. And so, as you know, this is a 1/2 power. So when you integrate, you get a 3/2 power, and you get a 2/3 coming out of that. Uh, and yeah, the y squared is treated as a constant with respect to integration by x. Next, we would evaluate this expression, x equals 1 and x equals 9. When you plug that in, you get, so I guess I don't really specify it out completely, but you would get, the 1 over y squared doesn't matter, and you would get 27 minus 1 when you evaluate. That's how you end up with the 26 out here. Now we then integrate this 1 over y squared, so that is y to the negative second power. When you integrate that, dy, you get negative 1 over y, and then evaluate. Yes. So that's why I end up flipping the evaluation. See, from 4 to 2, it became 2 to 4. That's because I'm absorbing that negative that popped out from integrating this y to the negative second power. So by absorbing that negative, I flip the evaluation order, and that'll leave me with 52 over 3, 1 over 4 minus 1 over 2, which gives me a negative 1 over 4. And, well, there's some simplification, 26, 13, yeah, so it does just become, well, I have it written there, it becomes negative 13 over 3 when you do the calculation. Okay. So, right, so these are the two problems, I think, that correspond to this section most. The way that the problem is phrased is it asks you to, I think it was to choose the order, or is it to switch the order? Okay, I did something similar to 19. That one says interchange the order. These two say choose the correct order. Right, and for me, the answer is that it's not about choosing the order. Well, I mean, with this one, it doesn't matter. So, because this is, you can kind of see that this is a product of a function involving x and a function involving y, right? The function itself is sine of ln of x over x, and this is a u sub. If you didn't spot it, you should have been able to spot it. This is a u sub, so you can compute that pretty easily. And just as a hint, in case you get stuck on it, you can. That's the answer for that. If you wanted to do it as an iterated integral, that's fine. It's just that the other thing is a constant, and so when you integrate, say with respect to x, then all the things involving y, you treat as a constant. You can pull it out of the integral. So that's just one step removed from the fact that you can split the entire integral into two separate integrals. Okay, and then this one, again, this is a product of a function involving x and a function involving y. So if you don't see that right away, well, I have an example that will show you that. So I guess I'm just modifying some numbers here. So this exponential, the point is that algebraically, this is the same as e to the x times e to the minus 3y, right? The fact that you have the same base, different exponents, you can add the exponents. That's one of those rules of exponents. And so once we have this product, well, we can then split this integral. Notice how I'm doing this, though. The bounds for x are coming from the bounds for x. Notice that this dx at the end matches up with this integral. I know that this is a mistake that students that first encounter this subject, students that first encounter this subject, they kind of mess this up. So it really is like it's nested. It's like I don't know what are things that are nested. The only thing that comes to mind is like onions, but that's not I don't know. So the innermost integral and the differential element, they sort of wrap together and are one thing, and then the outer ones pair up as well. So when we split this into a product of two separate integrals, right, these are the bounds for x. You can see that they're the bounds for x, and then these are the bounds for y. And so we end up with this integral times this integral. Well, this second integral should be pretty easy to do. It's simply an exponential. You would have to cancel this constant that would pop up from chain rule. If you were to differentiate this guy, you can see that a minus 3 would pop out. That needs to be canceled with this outer scalar. This one involves integration by parts. So I would hope that you remember this from Calc 2, but I know from experience that I need to recall this with you guys. So integration by parts. Well, there's different ways of expressing it. So integral u dv equals uv minus integral v du. That is the textbook way of explaining this. I just did a semester where Lena was using F's and G's instead of U's and V's, but it's the same kind of thing. And I also showed my students something called the DI method, which I would prefer to use, but whenever I use it, I basically need to give a brief explanation of the method. It is just another way of writing the work for integration by parts. So with integration by parts, you would normally need to you'd need to compute. Well, how should I say this? You would split your integral into two parts: a part that you differentiate, which you would call u, and a part that you integrate, which you would call dv. Okay, and then you would proceed to differentiate the u, and you would proceed to integrate the v, and you'd end up getting these things. And then you end up with u times. So then the integration by parts says it's u times v minus the integral of v du. Okay. Well, this kind of tabular arrangement of the information can be simplified even further to the point that you don't need the variables u and v. And that's what the DI method is, or the DI layout is about. You have a column that you differentiate and a column that you integrate. And then the last row, if such a row exists, if you don't have a zero here, basically, the last row is interpreted as an integral. The one additional piece of information you need is that there's actually sign alternation. So there's an additional sign column on the left. So I will just quickly do that here. And what you do is you would read off diagonals, and then if there is anything left over, this last row would be an integral. But we have a nice thing here where the differentiation column went to 0. So that integral is an integral of 0. That just gives you a constant. So you don't actually need to perform an integral there. You would have your integration constant showing up from that. So reading off the answer from, or the result from integration by parts, it says it's going to be x e to the x minus e to the x. That is the answer, plus c. That's the, oops. Yeah. That is the answer from doing the integral, from doing this integral. And that is exactly what I wrote here. If you ignore the plus c and if you factor out the exponential, you get x minus 1 times the exponential. Okay, then you do the evaluations. That's just going to be arithmetic. I'm not going to say any further about that. And you simplify and you get the result. Okay. Right. I think this is the last thing I mentioned, which is there are two. I mean, these are analogs of things that you know about integrals. So I think the first one. Well, in a sense, it's an analog. So if you had just like this, a to b, this is back from Calc 1, right? You know that. So it's the length of the interval that you integrate over for a one-dimensional integral. For a two-dimensional integral, it ends up being the area of the two-dimensional region. And you can imagine that for the three-dimensional integral, which we don't talk about yet, but I'll just mention it right now just to tell you that this property is a very general property. So this is also going to be measuring the volume of the region that you integrate over. So really, the integrating the function 1 is rather special. It measures the notion of area or volume for whatever dimension you're working in. So if you're working in dimension 1, integrating the function 1 gives you the length of the region you integrate over. In dimension 2, if you integrate the function 1, you're measuring the area of the region that you integrate over. And in dimension 3, if you integrate the function 1, you're measuring the volume of the region you're integrating over. Yeah, so it's it's whatever notion of area or volume makes sense for the dimension that you're working in. And in some sense, like this also has this is intuitively true, I think. If we kind of just draw the picture, so like you have some region R. If you're integrating the function 1, it's like you're saying that, well, this region, it has height 1, whatever it is, and well, the two-dimensional integral is measuring volume, okay? The volume of this region, which is going to be base times height. Well, the height is 1, so the volume, which is what the integral measures, is going to equal the area, because the height was 1. So hopefully that made sense. If not, I guess don't worry about it, but just know that, yeah, integrating the function 1 is going to correspond to calculating the area volume of the region. And now this other application. So the average value of a function over some region. So hopefully you remember from Calc 1 that there was a version of this in the one-dimensional case. The average value of a function over some interval, what you did was you integrated over that interval, and then you divided by the length of the interval. And the analogous thing is true in this two-dimensional case and in the three-dimensional case as well. You integrate over the region, and then you divide by the area of the region. The way I think about this is that it's a weighted sum. You Yeah, the actual value that the function takes at a point is the weight that you ascribe to that point. And then dividing by the area is to basically normalize things. So if the function was always 1, well, then you would end up just getting the value 1. You can see that there's an immediate cancellation there. If the function was the value 2, then it would be 2 times the area divided by area, which is going to be 2. Once you start deviating your function, you start having more weights on certain points than other points, then the average of the function is going to go up. Yeah, I don't know what else I can say about that. Well, you have a problem that uses this formula. So, given some function and some particular range or region, find the average value of the function over the region. So it is just using the formula. You compute the area of the region. Now, it's simple in this case. You can imagine that for later sections, for later problems, this region may not be a rectangular region like this. It'll be some more complicated region that you may not immediately know the area of, in which case you'd have to resort to doing this kind of integral in order to compute the area. But because we have a rectangle, we know right away that the area of this rectangle is 6. And so we have 1 over 6. We divide by 6 outside the interval. Okay. And we integrate this over this region. Okay. So first I write it without specifying any integration order. I'm just abstractly saying I'm integrating over the region R, this function. And then the next thing I do is I choose some order. It doesn't matter which order. I think that's pretty clear that whichever order, it'll be pretty straightforward. Both of these are power rules. So integrating with respect to x, x cubed over 3 for this term. This guy gets an x here. You can double check that. I mean, maybe it's a good strategy to always double check whenever you integrate that whatever you think is the result of integration, that you can take the partial derivative and get back to where you started, right? Remember that integrals and derivatives are supposed to be opposites. So you can always double check your work by doing the opposite and making sure you get back to where you started. So indeed, we do, right? When we take the x derivative, this will become y cubed. Okay, so then we evaluate, right? Specifically, we evaluate x from 2 to 3. Doing so, oh, that is a typo. Lots of typos. Okay, I will fix that when I upload the PDF. This should be 2, this should be 0. That is, wow. Okay, but I think that the evaluation is correct, because 0 gives you 0, and 2 will give you this expression. And I should probably put parentheses around here. Yeah, just to make it look a bit nicer. So then we have this, and then we integrate this with respect to y, which gives you that. And then you evaluate. So I didn't specify y here. I didn't think it was necessary to label this. You can if you want to. Say that this is y ranging from 0 to 3. You do the evaluation, and you get some number back out. And so there you have it. The average value for this function was this quantity. Okay, well, I guess that's all I've got for this.